Welcome. In this video, we're going to work with nth roots, simplify radicals, rationalize the denominator, and simplify expressions with radicals. So we have this expression, this nth root of a equal b. That means that b to the n would give us the number a. Now, if a is greater than or equal to 0 and b is greater than or equal to 0, then n is even. That's if n is even. That's true. And a and b are real numbers if n is odd. So let's look at the cube root of 27. Now I can rewrite 27 as the cube root of 3 being cubed. If these two numbers are the same, that means that we have a perfect third root here, and we would say the answer to that is 3. So the third root of 27 is 3. If I have the cube root of negative 27, that's the cube root of negative 3 being cubed. So the cube root of negative 27 is minus 3. So as you can see, these are real numbers. If I have the square root of 4, then it's going to equal 2. It has to be positive if we're talking about real numbers. So if I had the fourth root of 16, I could rewrite that as the fourth root of 2 to the fourth power. Because those are the same, that means I can pull out that base, that 2, and that would equal 2. What if I had the fourth root of 1 over 81? Well, I could rewrite that as the fourth root of 1 over 3 to the fourth power. So with those being the same, that means I can pull out the 1/3. If I had the sixth root of negative 4 to the sixth, I could rewrite that as the sixth root of negative 1 times 4 all to the sixth power. So negative 1 to the sixth power, 4 to the sixth power. But we know that negative 1 to the sixth power, because it's even, would just be 1. And that would be multiplied by 4 to the sixth power. And when my root is the same as the power, that means I can pull that base out. So that would just equal 4. So in general, we would say the nth root of a to the n equal a if n is greater than or equal to 3 and is odd. The nth root of a to the n is the absolute value of a if n is greater than or equal to 2 and n is even. And here are some properties of radicals that can be helpful. That if I have the nth root of ab, it's the same thing as taking the nth root of a times the nth root of b. If I have the nth root of the quotient a over b, it's the same as the nth root of a divided by the nth root of b, given b doesn't equal 0. And the nth root of a to the m is the same as taking the nth root of a and taking that to the m power. By convention, this is the square root. In other words, there would be a 2 written there, but it's used so often we don't usually write the 2. So our square root would look like this. And if I had the square root of 50, what I'd like to do is use some of the properties to help us to solve this. So I could rewrite the square root of 50 as 2 times 25. Well, we just learned that I could rewrite that as the square root of 2 times the square root of 25. I know that the square root of 25 is 5 squared. So in other words, 25 is a perfect square. So it is 5 being squared. So I could rewrite this as 5 times the square root of 2, since this equals 5. Let's look at another example. If I have the cube root of 54. Now it's nice if I can break 54 up into something to the third power. So I'm going to use my prime factorization to help me. So I know, if I look in here, I know 9 goes into here 6 times. 3 times 3, 2 times 3. So I could rewrite 54 as 2 times 3 cubed. So in here, 2 times 3 cubed, I break this up, the cube root of 2 times the cube root of 3 to the third. Again, when these guys match, it means I can pull out the base. So I'm going to pull out 3, and I'm going to place it in front of this cube root of 2. And I have my answer. What if I had something like the cube root of negative 24, x to the 5th, y to the 7th? Well, I would first work with my number 24, and I'd see how I could rewrite that in my prime so I can see where the powers are. So it's 2 times 12, 2 times 6, 2 times 3. So 24 is 2 to the third times 3. So I could rewrite this as negative 1 times 2 to the third times 3. Now negative 1, I can write that, well, think of this, negative 1 to the third equals minus 1, so I could rewrite this actually as negative 1 to the third, so I can truly see that whenever I have a negative, no matter what this is, I can pull it out. You know, if it's odd, I can pull it out as a negative 1. And then I have x to the 5th. Well, I want it in third, so I can break up x to the 5th as x to the third times x squared. And x to the 7th, y to the 7th, excuse me, as y to the third times y. So I could, like I said, I can break these up. So let me, because I'm running out of room here, we'll do that in my next one. So I'm going to pull out the 1. I can pull out the 2, since those are being cubed. And what I would have left in here is a 3, and then my x to the third, x squared, y to the third times y. That means this can come out because these are cubed. A y can come out and another y can come out. So my answer, negative 2x y squared, because I could pull out 2 y's. And then what's left under the radical is a 3, an x squared, and a y. My fraction here, so I could break this up as the 4th root, and on the bottom, the 4th root of 81 x to the 6th, 16 y to the 7th. Then, further, I know that if I look at 81, it's 9 times 9, or 3 times 3, 3 times 3, or 3 to the 4th. And then I have x to the 6th. I want to break that into anything with the 4th and then whatever is left over. So that's x to the 4th, x squared. On the bottom, I have 16. And I know 16 is 2 to the 4th, because I know it's 4 times 4. And I'd have my 2 to the 4th. Then y to the 7th, I'm going to break it up. I have y to the 4, and I'd have left over 3. This can come out, this can come out, this can come out, and that. But I have to be careful with my variable. So if it's x to the 4th, I'd have to write it, when we do this, the 3 comes out, that base comes out, then the x comes out, but I need to put that in absolute values because we have an even root. And what remains under the radical is x squared. We do the same thing here. 2 is going to come out and one of my y's. So I have 2, absolute value of y, and inside here, since these are the 4th root, my y to the 3rd remains. You could either keep it like this, or you could write it as 3 absolute value of x over 2 absolute value of y, the 4th root of x squared over y cubed. It doesn't matter. Either one would be correct. Let's look at if we have a equation with radicals. So if I had -4 square root of 20 plus square root of 5. What I'd have to do is I'd have to see if there's any way to make these radicals the same. So I go off to the side and I say, okay, if I have the square root of 20, I know that that is 4 times 5, or 2 squared times 5. I could pull out a 2 and have 2 times the square root of 5. So I'm going to replace the square root of 20 with 2 times the square root of 5. When I do that, I'd have -8 times the square root of 5 plus the square root of 5. -8 square roots of 5 plus 1 square root of 5 would give me -7 square root of 5. That's combining like radicals. So let's look at this example. So I've got cube roots of all of these. So I'm first going to look at this one right here, this cube root of 8x. I know I can rewrite 8 as 2 to the third, so I could rewrite this as 2 to the third times x. With the second ones, I know that that's a -1, but it's to that cube root, so we know we can pull the minus out. So I'd have -1 times the square root of x. On this third one, I have to think about 64. 64 is, so we have 8 times 8, and we know that this is 4 times 2, 2 times 2, and over here, same thing. So we actually have this as 2 to the third times 2 to the third. So I could rewrite this as the cube root of 2 cubed times 2 cubed. And then I have x to the fourth. I could break that up as x cubed with the remaining x inside. Just another x rather. So I pull out everything that has the same power as the cube, as the root that I have. So that means I can pull out a 2. And inside I'd be left with an x. I have this -5 square root of x. Can't do anything there. But with this one, I can pull out a 2. I can pull out another 2, because those are the same, and an x. And I'd have the cube root of x. Cleaning things up a little bit, 2 times 2 is 4, cube root of x. So I have this in here. So I have 2 cube roots of x minus 5 cube roots of x. So this would give me -3 square root of x plus 4x times the cube root of x. And these are cube roots. I didn't mean to drop off the 3's in here. Okay. And if I take a cube root of x out of here, I'd have -3 plus 4x. So now we're going to talk about rationalizing the denominator. We never like to see radicals in the denominator. So if I had something like this, I have to think of myself, what can I multiply the square root of 2 by to get rid of that radical? Well, we know we could multiply it by the square root of 2, right? But what we do to the bottom, we have to do to the top. So on the bottom, I have the square root of 2, square root of 2, which gets rid of the radical. We know that gives us 2. And on top, square root of 2. And now we have rationalized the denominator. If I had 1 and the cube root of 2, well, I would need, in order to get rid of this radical, I'd have to multiply by 2 squared so that I would have 2 to the third in there. What I do to the denominator, I have to do to the numerator. So I'd have 3 times the cube root of 2 squared is 4. And then this would give me the cube root of 2 cubed, which would be 2. So my answer is the cube root of 4 divided by 2. And that's how we rationalize the denominator. So let's look at a couple more examples. So if I had, let's say 3 times the 5 times the square root of 2, I want to get rid of that square root of 2, so I'm going to multiply top and bottom by square root of 2. And I'd have 3 square roots of 2 times 5. And the square root of 2 times the square root of 2 gives us that 2. That's what we were going for. So we'd have 3 times the square root of 2 over 10. Now what if the denominator is a little bit even more complicated? So I had something like this. 1 over 1 minus the square root of 2. Now I've got to think, what can I do to get rid of that square root of 2? And if you think, okay, I'm just going to multiply by the square root of 2. Top and bottom. But remember, when you multiply, you have to multiply the whole denominator by that. So this would be square root of 2. Square root of 2 times 1 would be square root of 2. Minus 2, we've made it worse. So we can't do that. And remember, you can't say 1 and 1 over 1 minus 2. We can't do that. That's illegal. So can't do that. So then I have to think, would I do that? And it goes back to the very important difference of squares. We know that that's a plus b, a minus b. So with this in mind, I can get a squared minus b squared here. That would work out great for us. So if I had a minus b, a plus b, where my a is 1 and my b is square root of 2, multiply the top by this, I would get 1 plus square root of 2 on top, because 1 times this, and then this is plus and minus. We're going to get the difference of 2 squares, so 1 times 1 is 1, minus square root of 2 times square root of 2 is 2, and that's exactly what we wanted. We now just have a number on the bottom, -1, or we could say -1 minus square root of 2, because remember, if you have a negative there, a number there, you'd have to put it over that and over that. So we could rewrite it like this. So if I had something like this, I'd multiply top and bottom by 3 square root of 3 minus 5. On the top, square root of 3 minus 5. And I'd work this out. So I'd say 4 minus the square root of 3. 4 minus 5 is a -20. And then on the bottom, square root of 3 times the square root of 3. Minus 5 times positive 5 is -25. So 4 square roots of 3 minus 20. 3 minus 25. I get -23, 4 square roots of 3 minus 20. Then I realized that 2 can go into all of these. So I could pull out a 2 here, and I'd have 2 times the square root of 3 minus 10, and 2 times -11. So I'd have 2 times the square root of 3 minus 10 over minus 11. And this brings me to a point. Generally, when I work on a problem like this, I wouldn't have distributed first. I would have left it as 4 times square root of 3 minus 5. Rationalize that denominator knowing it's the square of the first, so that would have been a 3 minus 25. This would have given me 4 square root of 3 minus 5, and over this -22, and I would have seen right there how I would have seen 2 goes into there, 2 goes into here. So I would have 2 times square root of 3 minus 5 over 11, -11. And sometimes when the numbers get big, it's really nice to see that. So I generally try not to distribute through like this. I wait until the end. So if I had the square root of 7 divided by the square root of 2 plus 9, I'm going to multiply top and bottom, and we call this the conjugate. If this is square root of plus 9, then square root of 2 minus 9 is its conjugate, that opposite sign. So I'd have 7 times the square root of 2 minus 9, square of the first. Square of the first would be the square root of 2 squared, which would give me 2. Square of the second, 81. So I'd have 7 square root of 2 minus 9, 79 in here. And nothing can go into this, so we'd leave it just like that to see that it's totally factored in there. So there's working with our rationalizing the denominator. So thanks so much for watching.